So in today's session, we'll be seeing assertion recent questions on magnetic effects of current. All right. So let us go to the paper right away. Question number 11, assertion. Voltmeter is connected in parallel with the circuit. Voltmeter is connected in parallel with the circuit. Resistance of voltmeter is very large. Voltmeter and ammeter. How do you connect a voltmeter? For example, I have a circuit here. Look at this. This is a resistor. And I have a cell here and I have a switch here, right? I need to find the current and voltage in the circuit. So again, I have a circuit here. The circuit consists of a resistor, a cell and a switch. I need to measure the current and voltage in the circuit. Okay, if I want to measure the current, I'll connect the ammeter in series while the voltmeter is always connected in parallel. Can you tell me why? Voltmeter is always connected in parallel. We have discussed this in class. Voltmeter is always connected in parallel while ammeter is connected in series. There is a particular reason for this. I'll tell you. Look at this. You remember the conversion of galvanometer to ammeter? Conversion of galvanometer to ammeter. You know, this is a galvanometer. Okay? Galvanometer. And this can be converted to an ammeter by connecting a low resistance in parallel. Right. You remember? This is a galvanometer with a certain range. The range of the galvanometer is Ig. The current it can measure is Ig. Okay. I'm going to increase the range of this galvanometer. Right. This galvanometer can measure current up to Ig. I'm going to increase the range of the galvanometer or conversion of galvanometer into ammeter. Now, if a main current I comes in, tell me what happens. This is what? A low resistance connected in parallel. The low resistance is called shunt resistance. Shunt resistance. Okay, you are shunting. Shunting means bypassing. Shunt resistance. Okay, so this is a shunt resistance connected in parallel. What happens now? The current flowing through this is I minus Ig. I minus Ig. Okay, I minus Ig. And this current is S. This resistance is S. And you remember this? What is the effective resistance here? What is the effective resistance here? These are in parallel combination, right? S and G are in parallel combination. So R effective is equal to S into G by S plus G. Parallel combination. And the effective resistance is a very, very, very small value. Why? The shunt resistance itself is very small. And if you connect that in parallel, the value will be even less. I'll tell you the reason. Look at this. I have 2 ohm. I have 3 ohm. These are connected in parallel. What is the effective of these two? 2 into 3 by 2 plus 3. R1, R2 divided by R1 plus R2. That is how parallel combination is taken. Effective in parallel combination, I have 2 and 3. 2 into 3 by 2 plus 3. That is 6 divided by 5. It is 1.2. Just imagine I got 2 resistances. One is 2 ohm resistance. Second is 3 ohm resistance. And these are connected in parallel. I need to find the effective between A and B. Right. How do you find the effective between A and B? R1, R2 by R1 plus R2. That is 2 into 3 by 2 plus 3. That is 1.2. What do you understand from this? The effective is 1.2 and it is less than the lesser value here. Lesser value is what? Out of 2 and 3, the lesser value is 2. The effective is actually less than the least. That's a key point. We have written that in the note. You check the notes, it is there. Whenever resistors are connected in parallel, the effective value is less than the least. Whenever resistors are connected in parallel, the effective value is less than the least. For example, if 2, 3, 4, 5, 6, these are connected in parallel, the answer will be less than the least. Just give me a second. So this is galvanometer to ammeter conversion. How do you convert galvanometer to ammeter? It's a low resistance connected in parallel. Low resistance is also called shunt resistance. Shunting means bypassing. This resistance is actually low resistance. And what is the effective of these two? R1, R2 by R1 plus R2. S into G by S plus G. That's going to be even less. Why? You know, look at this 2, 3, 4, 5, 6. These resistors are connected in parallel. The effective will be less than 2. So when resistors are connected in parallel, that's a standard result. You check your notes, it is there. When resistors are connected in parallel, the effective resistance is less than the least value. Least value is 2 here. So the final answer will be less than 2. Less than 2. Okay. So when you connect these two together, S and G, effective will be less than R. Effective is actually what? Less than S. S itself is very small. So my point is, ammeter is a low resistance equipment. Ammeter is a low resistance equipment. Low resistance. So never ever forget this. Ammeter is low resistance equipment. Ammeter is a low resistance equipment. Why? Look at this. Even S is very small. Shunt resistance is very small. So effective resistance is less than that. So it's a very low resistance. So ammeter is a low resistance equipment. That is why this is always connected in series. Now think about voltmeter. Voltmeter. How about voltmeter? Voltmeter, I can do this here. Galvanometer to voltmeter. Galvanometer can be converted to voltmeter by connecting a high resistance in series. By connecting a high resistance in series. You are connecting a high resistance there. Okay. So it's already high resistance. So the effective will be what? They are in series, as you can see, G plus R. That will be greater than R. So effective resistance is large. So voltmeter is what? Voltmeter is a high resistance equipment. Never ever forget this. Okay. So voltmeter is high resistance equipment. So if you connect that in series, there will be voltage drop across it. Understood? There will be voltage loss across it. This is why voltmeters are always connected in parallel. Did you understand the point? Ammeter, we have written this in class. Ammeter is a low resistance equipment. Why? Because you are connecting a shunt resistance there. Shunt itself is very small. So the effective is less than that. My point is ammeter is a low resistance equipment. So it can be connected in series. No problem with it. It's a low resistance equipment. You want to measure current with it, right? You're expected to measure current with it. And then voltmeter. How about voltmeter? Galvanometer to ammeter conversion is done this way. Galvanometer, series connection, high resistance. A high resistance is connected in series. Here it is low resistance connected in parallel. Here it is high resistance connected in series. So voltmeter is a high resistance equipment. So if you connect voltmeter in series, what happens if you connect a voltmeter? It's a high resistance equipment. There will be a lot of voltage drop. Okay, so a great large voltage drop there. So instead you connect it in parallel. Let's go back to the question and check it again. What is there in the question? Tell me, could you please read the question? Assertion, voltmeter is connected in parallel with circuit. Assertion is true. Voltmeter is connected in parallel. Assertion is true. How about reason? Let us look at reason. Resistance of voltmeter is very large. Resistance of voltmeter is large. It's a large resistance, right? Yes, assertion is true. Reason is true. And reason correctly asserts the first statement, right? Reason is the correct explanation. So option A is correct. Assertion says voltmeter is a high resistance equipment. Reason says, sorry, voltmeter is what? Assertion says what? Voltmeter is connected in parallel. And reason says what? Resistance of voltmeter is large. Yes, it is because of the second statement that the first statement is done. Understood? Or first statement has its reason in the second statement. Am I correct? First statement becomes relevant because second statement is true. Second statement states what? It states that resistance of voltmeter is large. Yes, since the resistance of voltmeter is large, this is connected in parallel. Answer is option A. Did you understand? So let's move to the next question now. Question number 2. Read question number 2. Read question number 2. All right. Question number 2. 12. Magnetic field lines can entirely be confined within the core of the toroid, but not within a straight solenoid. So magnetic field lines can be entirely confined within the core of a toroid, but not within a straight solenoid. What is a toroid? What is a solenoid? You know what? A toroid is actually a bent solenoid. This is how a toroid would look like. It has what? It has coils wound over a ring like this. Okay, circular core like this. Current is entering, current is exiting. So this acts like a magnet, right? And toroid has magnetic field lines confined within it. All the magnetic field lines are axial. All the magnetic field lines are confined. And what is a magnetic field line? Magnetic field strength mu0 times Ni. where n is number density, number of turns per unit length. And this is called a solenoid, where the field lines are not confined. Why? Some of the field lines are actually passing outside the solenoid. Here, all the field lines are confined. What is magnetic field here? Here also magnetic field is mu0 times Ni. So this is called a toroid. This is called a solenoid. Okay, you take a pipe and wind wires over it. That becomes a solenoid. And for a solenoid, the magnetic field inside is mu0 Ni, where small letter n is the number density, number of turns per unit length, number of turns per unit length. And if you bend it so that the ends meet, that becomes a toroid. So you can say that the toroid is an endless solenoid. Toroid is an endless solenoid. Okay, so where is the field confined? Look at this, the field lines are inside. So when you bend it over, you know, when you join the ends together, the magnetic field is perfectly confined within it. Look at this, the magnetic field lines are all inside. Magnetic field lines are all inside, but not for a solenoid. For solenoid, majority of field lines are inside, but some are still going outside. Let's look at the question. Let's look at the options again. I mean the statements. Magnetic field lines can be entirely confined within the core of a toroid. That's right, but not within a straight solenoid. So assertion is true. What does assertion say? Assertion says what? The magnetic field lines can be entirely confined within the core of the toroid. Can be entirely confined. That's right, but not within a straight solenoid. Straight solenoid is not possible. Cannot be confined. So assertion is right. Now, reason, the magnetic field inside the solenoid is uniform. That's also true. Inside the solenoid, magnetic field is uniform, but outside it is non-uniform, right? Inside it is uniform. How do we know if it is uniform? All are straight lines, right? And equidistant lines. So that is a uniform field inside. But is that the reason? Assertion is true, reason is true, but reason doesn't explain assertion. So answer is option B. Is it because of the uniform nature that it can't be confined? No, that is not the reason. You didn't understand. I'm repeating the statements one more time. Statement number 1 is correct. Assertion is correct because assertion says that in a toroid, magnetic field can be perfectly confined inside the core, while in solenoid it is not possible. Yes, that is true. Okay. Reason says that the solenoid has uniform field inside. Yes. How do we know? Look at the lines. All the lines are parallel. All the lines are straight lines. All the lines are equidistant. This is called a uniform field. Be it a magnetic field or electric field, this can be called a uniform field. How do we call it uniform field? Because all the lines, why do we call it uniform field? Because all the lines are parallel, all the lines are straight, all the lines are equally spaced. Look at this, the distance is the same, equidistant lines. Understood? So inside it is uniform field. Second statement says that inside it is uniform field. Now, is it because of that the first statement is coming up? No, first statement has no relation to second statement. It is not because that the uniform field is there that the field cannot be confined here. Understood? Did you understand? So answer is option B. Is that clear? Question number 12 we did. The answer is option B. Question number 13. An ammeter is connected in series with AC circuit. An ammeter is connected in series with AC circuit. How is an ammeter connected? How is an ammeter connected? Do you remember? Ammeter is always connected in series, right? Ammeter is always connected in series. So assertion is true. Ammeter is connected in series because it's a low resistance equipment. Let us see. Reason. Ammeter is high resistance galvanometer. That is wrong. Ammeter is what? Ammeter is what? Ammeter is a high resistance. I mean, is ammeter high resistance equipment? Read assertion statement. Ammeter is connected in series. Yep, that's right. Ammeter is always connected in series. Voltmeter is connected in parallel. Ammeter is connected in series. So assertion statement is true. Let us look at reason statement. Ammeter is a high resistance galvanometer. That is absolutely wrong. Ammeter is a low resistance equipment. Reason is false. Assertion is true. Reason is false. Answer is option C. I'm giving you 5 seconds pause to ask me questions. Tell me if you didn't understand, I'll repeat. Okay, fine. Right. So that is question. So answer to question number 13 is option C. Question number 14. Read question number 14. There is a spark in the switch. There is a spark in the switch when the switch is closed. Current flowing in the conductor produces magnetic field. Read that again. Actually, that statement is that key given there is wrong, it seems. Assertion, let us see. There is a spark in the switch when the switch is closed. Actually, a spark is produced when a switch is made open. Do you remember? I have told you during electromagnetic induction, discussions on electromagnetic induction. Look at this. This is a switch. That is how kitchen gas cylinders explode. Understood? You know, the gas will be leaking and suddenly you are getting in and turning one switch off. There is a spark, boom, it explodes. Understood? So why does it happen? Because when you break the circuit, when you switch it off, you are breaking the circuit. Correct? See, this is one switch, any power switch you have at home, and you are switching this off. What happens now? You have broken the circuit, so current decreases. Current decreases means field decreases. Field decreases means magnetic flux decreases. So Faraday's law says that EMF is induced. Lenz's law says that EMF should oppose the cause. Here the cause is switching off. So it will try to re-establish the current by sending a spark across the switch. Actually, when you turn the switch off, you know, spark is produced. Understood? Turning the switch off, the spark is produced. But while turning the switch on, spark is never produced. I don't know why they have given option B there, but assertion statement seems to be wrong. And if there is a change, I'll update. Assertion is false there. And how about reason there? Reason, let us read reason. Current flowing in a conductor produces magnetic field. That is true. But such an option doesn't exist. So there could be something wrong with the question. Assertion is false, reason is true. Such an option is not there. Look at the directions. Like I told you, sometimes this option can be there, but we have been given only 4. Assertion is true, reason is true, reason is the correct explanation, option A. Assertion is true, reason is not the correct explanation, option B. Assertion is true, reason is false, option C. Assertion and reason are false, option D. But there can be a 5th option. Assertion is false, reason is true. But in this case, they haven't given it. So let us read that statement one more time. There is a spark in the switch when the switch is closed. Switch is closed means made on. Closed means what? A switch is closed means what? Closed means it is made on. But while switching the circuit on, there is no spark. Spark is produced when switch is made off. So that statement is wrong. When a switch is made off, there can be spark. We even saw one video on this. I don't know whether you remember or not. When you turn the switch off, there is a spark. Why is a spark there? Because when you switch it off, the current suddenly drops. Current decreases. So magnetic field decreases. So magnetic flux decreases. Faraday's law says that the flux decrease should induce an EMF. And that EMF by Lenz's law should oppose the cause. Here the cause is current decreases. So current has to be re-established. This is why a spark is sent across the switch. Okay, so here assertion is false and reason is true. Reason is true. Okay, such an option doesn't exist. You just mark it there. Did you understand? Any questions here? While switching on, sparks can't be there. Okay, sparks are seen while switching off only. So there must be something wrong with the question. Okay. When you switch it off, you are cutting the circuit. When you switch it off, you are cutting the circuit. So current decreases. Current decreases. Current here decreases. Magnetic field decreases because current produces magnetic field. So flux decreases. Flux is another term for magnetic field. When flux decreases, an EMF is induced. That EMF should oppose the cause. Cause is decrease of current. So current has to be re-established. That is done by giving a spark across a switch. So answer is option. Option can't be there. Okay. So let us go to question number 14. Oh, 14 we did. Question number 15. Read question number 15. Assertion. The magnetic field intensity at the center of a circular coil carrying current changes if the current through the coil is doubled. The magnetic field at the center of a coil. You know, look at this. This is coil. Do you remember the magnetic field at the center of the coil? You remember the equation? Mu 0 by 4 pi. Magnetic field. Mu 0 by 4 pi into I by R into 2 pi. That is how we take it. Magnetic field at the center of a circular coil. I gave you 5 systems. I don't know if you remember or not. Magnetic field due to finite conductor, mu 0 by 4 pi into I by r into sine phi 1 plus sine phi 2. Both ends to infinity, 2. One end to infinity, 1. Circular arc, it is alpha. Full circle, it is 2 pi. Anyway, forget about that. That is there in the numerical discussion session that we did. So this is what? Magnetic field at the center of a coil. Magnetic field at the center of a circular coil. Circular coil. What is it? Mu 0 by 4 pi into I by r into 2 pi. This and this are cut. It is mu 0 I by 2r. You learned this in school classes, right? Mu 0 I by 2r. Let's look at question number 15 again. The magnetic field intensity at the center of a coil carrying current changes if the current through the coil is doubled. Yes, because magnetic field is proportional to I here. Look at that. Obviously, when the current changes, the magnetic field also changes. So assertion is true. Assertion is true. Let us look at reason now. The magnetic field intensity is dependent on current in conductor. Yes, magnetic field is dependent on current in conductor. So reason is also true and it correctly explains assertion. So answer is option A. Did you understand that? I'll repeat one more time. What is the first statement? The magnetic field intensity at the center of a circular coil. Magnetic field at the center of a circular coil is what? Mu 0 I divided by 2r, where r is the radius. Okay. And what does it say? What does it say? The magnetic field at the center of coil changes if the current through the coil is doubled. Yes, if the current is doubled, the magnetic field also gets doubled. That happens because B is proportional to I. Second statement, magnetic field intensity is dependent on current in the conductor. Yes, magnetic field is dependent on current. Right, so assertion is true, reason is true, and reason is the correct explanation for assertion. Correct. Because reason says what? Magnetic field is dependent on conductor. That is exactly what explains the first statement. Correct. First statement states what? Magnetic field changes as current changes. Second statement says what? Magnetic field is dependent on current. So that is why the first statement comes. Am I correct? Did you understand? Say something, please. Everyone, please. This is a formula that you learned in classes. Mu 0 by 4 pi into 2 I by r into 2 pi. That is the equation for magnetic field at the center of a circular coil. Center of the circular coil. That's a standard formula. And then 2 pi and 2 pi are cut. You are getting mu 0 I by 2r. You must have seen this form, right, in school. Understood? Okay, fine. So assertion is true, reason is true. Both reason correctly explains assertion. So answer is option A. Look at the next question. Question number 16. Assertion. When a charged particle moves perpendicular to magnetic field, kinetic energy and momentum gets affected. Very important point. We have done this at least twice in class. Read question number 16. When a charged particle moves perpendicular to a magnetic field, kinetic energy and momentum gets affected. Look at this. Charged particle moves perpendicular to magnetic field. This is a magnetic field, right? Magnetic field, and a charged particle moves perpendicular. Look at that. What happens to it? As it enters the magnetic field, it experiences Lorentz force. Lorentz force is usually centripetal force. Lorentz force acts as centripetal force because Lorentz force is Q into V cross B. This is called a Lorentz force. Whenever a charged particle like a proton, electron, deuteron, alpha particle, triton, there can be different charged particles, right? Whenever a charged particle enters a magnetic field, it experiences a force called Lorentz force. Lorentz force is given by Q into V cross B. And Lorentz force, as you can see, is directed towards the center. Lorentz force. So that force is acting as centripetal force. Obviously, there will be a circular motion. Understood? Obviously, there is a circular motion. Right. So whenever the particle enters, there is a circular motion. But look at that. Is the velocity, is the speed changing? Speed doesn't change. Speed doesn't change. Why? Because it is centripetal force. I told you the reason. This is a previous board question. Why does the speed remain unchanged? As it enters, speed remains unchanged because the kind of force that acts here is centripetal force. Centripetal force can only change direction. Centripetal force cannot change magnitude. Understood? So speed not change to speed, but velocity changes. Velocity alone changes. Look at that, because velocity here is in this direction, here is in this direction, here is in this direction. So velocity keeps changing as direction keeps changing, but speed remains constant. And then kinetic energy. How about kinetic energy? Kinetic energy is half mv square, where v is not velocity, v is actually speed. Since speed is constant, kinetic energy is also constant. Show that kinetic energy is a constant for a particle entering a magnetic field, charged particle entering a magnetic field. That's a very important question. We have done this in two methods, by two methods. I've done this question by two methods. Okay, check the notebooks. It is there. All right. I'll quickly explain that one more time. Give me a second. All right. So this is what? This is a charged particle. When I say charged particle, it can be an electron, a proton, deuteron, alpha particle. There can be different particles, right? And the particle enters the magnetic field. When it enters the magnetic field, a force begins to act. That is called Lorentz force. Lorentz force always acts as centripetal force. Centripetal force is to the center. Here it is to the center. Here it is to the center. Here it is to the center. Centripetal force is always to the center. Okay. Why does it act as centripetal force? There is a reason for that which you are not expected to know. V cross B will be perpendicular to F all the time. V will be perpendicular to F. That means velocity is here. So force should be perpendicular to it. So it is centripetal force all the time. Just know that it is centripetal force. So it actually takes a circular path like this. But while doing this, the speed remains unchanged. Speed is constant. Speed is constant. Why is speed constant? Because no work is done. Centripetal force does zero work. Oh, tell me what, you learned that in first year classes. This is the displacement. This is the force. What is the display angle between them? 90 degree. So work done is what? FD cos 90. Cos 90 is 0. So work done by centripetal force is 0. You proved this in first year classes. Work done by centripetal force is 0. So here also work done by the Lorentz force is 0. If work done is 0, there is no change in kinetic energy, right? See, work done is 0. So change in kinetic energy is what? 0. Because work done is converted to change in kinetic energy. If no work is done, no change in kinetic energy. So speed is a constant, hence kinetic energy is a constant, but velocity is different. Velocity keeps changing, right? Because velocity at different points will be different. Why? Because directions are different, as you can see. Direction of velocity is different. That happens because of centripetal force. Let us look at the statement one more time. Question number 16 one more time. Read question number 16. When a charged particle moves perpendicular to magnetic field, its kinetic energy and momentum gets affected. That's wrong. Kinetic energy never gets affected. Kinetic energy remains same. So assertion is false. What about reason? Let's see reason. Question number 16. Force changes velocity of charged particle. Force changes velocity of charged particles. That is also true. That is true. Force changes velocity of charged particle. Velocity changes. I don't know. That is also wrong. Assertion is false. Reason is true. Such a case is not there. But you know, reason is true. Force changes velocity of charged particle. Velocity changes because what? Velocity changes because of what? Velocity changes because of what? Velocity is a vector quantity. It changes even when the direction changes. Here the direction is changing, right? You don't understand? What does the second statement say? Could you please read the second statement? Is it my problem? Question number 16. Second statement. Force changes velocity of charged particle. Force changes velocity. Obviously, it changes velocity. Because velocity is a vector quantity. It can change when the direction changes. Obviously, the direction keeps changing, right? Yes, so that statement is true. Reason is true. But assertion is false. Assertion says what? Charged particle moves perpendicular, then kinetic energy never gets affected. So assertion is false, reason is true, but such an option doesn't exist. I'm going to put that as option E. Option E. Did you understand? Again, they might have gone wrong with the question. Did you understand? If you have any disagreement, tell me please. You can tell me the difference of opinion anytime, because assertion reason questions are to be done like that. Understand? You can raise a point all the time. I have to check if I've gone wrong. Let me see once again. When a charged particle moves perpendicular to a magnetic field, charged particle moves perpendicular to a magnetic field, then its kinetic energy and momentum gets affected. Momentum gets affected because mass into velocity. Momentum gets affected. But kinetic energy, does it get affected? No, kinetic energy is constant. I'm damn sure about it. Kinetic energy is a scalar quantity. Half m into speed square. It's not velocity square. Half m speed square. Speed is constant. So kinetic energy doesn't get affected. Statement number 1 is correct. Statement number 2, force changes velocity of charged particle. Yes, force changes velocity of particle because velocity changes because the direction changes. Velocity is a vector. It changes even when the direction changes. If they say speed, that is wrong. Speed. Okay, but speed doesn't get affected, but force changes the velocity of charged particle. That statement is true. Did you understand? Question number 17. In electric circuits, question number 17. Look at question number 17. In electric circuits, wires carrying currents in opposite directions are often twisted together. Yes, in electric circuits, wires are usually twisted together like this. Twisted together like this. Now, assertion in electric circuits, assertion statement is what? In electric circuits, wires carrying currents in opposite directions are twisted together. That's right. Wires are twisted, paired together. Reason, if the wires are not twisted together, the combination of wires form a current loop. Combination of wires forms a current loop. The magnetic field generated by the loop might affect adjacent circuits or components. Yes. So in order to eliminate the effects on the nearby circuits, so reason statement is also true and assertion is properly explained by reason. So answer is option A. I'll repeat the statement one more time. We are on question number 17 now. 17. In electric circuits, wires carrying currents in opposite directions are often twisted together. Wires are often twisted together, carrying currents in opposite directions. Yeah, that's right. Wires are twisted together. That is correct. Why is it done? Let us see reason. If the wires are not twisted together, so that obviously leads to the reason, right? The combination of wires forms a current loop. The combination would form a current loop. The magnetic field generated by the loop might affect adjacent circuits or components. Okay. So if they are not wound like this, if they are not twisted like this, they may form loops and they may create magnetic field. And then what happens? That will affect the nearby circuits. But if they are wound in this direction, their inductions will cancel each other. One is carrying current in upward direction, the other is carrying current in the downward direction, right? You remember non-inductive winding you learned in electromagnetic induction? Check the notes, it is there. Okay. So one current is in the upward direction, one current is in the downward direction. They are anti-parallel. Their fields, their inductions will cancel. So that is reason statement is also true. And see if reason correctly justifies assertion. Yes. Reason says if the wires are not twisted together. So obviously that must be the reason. Correct. So answer is option A. Answer is option A. Did you understand? Waiting for your responses. Tell me please, I need everyone to respond. All right, question number 19. Oh, question number 18. When two long parallel wires hanging freely are connected in parallel to a battery, when two long parallel wires hanging freely are connected to a battery like this, they come closer to each other. Read it again. Assertion statement is what? Assertion statement is what? Read the assertion statement again. 18th question. When two long parallel wires hanging freely are connected in parallel to a battery, They come closer to each other. Let us see if it is correct or not. Look at this. What is the direction of current? From positive to negative. So this is the direction of current. From positive to negative, this is the direction of current. These are like currents, right? Like currents, right? Like charges repel, like charges repel, like poles repel, but like currents attract. Do you remember? Do you remember? Like charges, plus and plus repel, minus and minus repel, like poles repel. North pole and north pole, they repel. South pole and south pole, they repel. Like currents, they attract each other. So these currents attract each other. So the force is downward, force is upward. So there is attractive force. They are like currents, right? They attract each other. So they come closer. Assertion statement is then what? Assertion statement is when two parallel wires hang freely are connected in parallel to battery, they come closer. That is true. Assertion statement is true. Let us see recent statement. Recent statement. Wires carrying current in opposite direction repel each other. Wires carrying current in opposite direction repel each other. Unlike currents. This is wires carrying currents in opposite direction. Yeah, they repel each other. That is also true. But does it explain the first statement? First statement says about attraction. Second statement says about repulsion. So second statement doesn't explain the first statement. Answer is option B. Is that clear? No. Read it again. Read it again. Okay, question number 18. When two long parallel wires hanging freely are connected in parallel to a battery. Two wires are connected in parallel to a battery. Okay, parallel to a battery. And then current is going from where to where? Positive to negative. Positive to negative. So the currents are going in these directions, right? Okay. Parallel to battery, they come closer to each other. Let us check if it is correct. They come closer. Do they come closer? These are like currents, like poles repel, like charges repel, but like currents attract each other. These are attracting each other. That is why they come closer. We are talking about them coming closer, attractive force. But second statement is about what? Look at second statement. Wires carrying current in opposite direction repel each other. That is also correct. Unlike currents repel each other. That's also correct. But that doesn't explain the first statement. First statement is about attraction. Second statement is about repulsion. So second statement doesn't explain first statement. Answer is option B. So sorry, option B. Did you understand? Please, please, please. I'm asking everyone. Tell me. So let's look at question number 19, 20. When question number 19, assertion statement. Let us read the assertion statement on question number 19. When the observation point lies along the length of the current element, magnetic field is 0. Observation point lies along the length of the current element. Look at this. You know, this is a current element. This is a current element. Current element is what? Current element is what? It's a small element carrying a current. Current element is what? Current element. It's a small element with a current. Current element, ideal. That creates a magnetic field over here. Look at this angle theta. What is a magnetic field there? We have Biot-Savart's law, which says that it is mu 0 by 4 pi ideal sine theta by r square. Okay. So magnetic field due to a current element is what? Magnetic field due to a current element. This is a current element, a small segment of a wire, small cut piece of a wire. Okay. That is called current element, carrying a current. It's called a current element. That is creating a magnetic field here. How much is the magnetic field? Biot-Savart's law says that the small magnetic field, dB is called small magnetic field, is mu 0 by 4 pi ideal sine theta by r square. Now take this point over to this conductor. Just imagine this point goes to this conductor. Okay, so what happens then? This line will come here like this, like this, like this, like this, like this, and it will coincide with the element. Theta would be what then? 0. Sine 0 would be what? 0. That is why we say magnetic field on a conductor is 0 due to current in itself. Magnetic field on a conductor due to current in itself is 0. Let us check the statements now. Question number 19. When the observation point lies along the length of the current element. Observation point lies along the length. For example, if a conductor goes like this. Here the field will be 0, here the field will be 0, here the field will be 0, here 0, here 0, due to this conductor, okay? Due to this conductor there will be field. So when extended, if it touches the point, those points are having zero field, along the length of the conductor. Wherever you go, the field would be equal to 0. Let us check it out one more time. Question number 19. Question number 19. When the observation point lies along the length, here, wherever it is, along the length. Along the length means theta would be 0, field would be 0. So assertion statement is true. When the observation point lies along the length of the element, magnetic field is 0. Assertion is true. How about reason? Magnetic field close to current element is 0. Magnetic field close to current element is at 0? No, that is false. So answer is option C. No matter how close it is, there will be a finite value of magnetic field. Understood? Yeah, sure. Shobhi. Right, no issues. Right, so assertion is true. Look at question number 19 again. When the observation point lies along the length of the conductor, magnetic field is 0. Assertion is true. What does the reason say? Reason says that magnetic field close to the current element is 0. Magnetic field close to the current element is at 0. That's very strong actually. Magnetic field on the conductor is 0. On the current element is 0, but magnetic field close to the current element is never 0. This is actually a strong value. When you come closer, the strength increases. So statement number 2 is false. Assertion is true. Reason is false. Answer is option C. Is that clear? All right. Question number 19 we did. Question number 20. That also we did in class. Check the class notes. It is there. Question number 20. A solenoid tends to expand when a current passes through it. The two straight parallel metallic wires carrying current in the same direction repel each other. So let us look at that. Current in same direction. Solenoid. Look at the solenoid. This is a solenoid. Now this is a cell and a switch. What happens when you let a current pass through this? Current is flowing like this. So if you consider two nearby rings, this side of the ring has clockwise current, while this side of the ring has anti-clockwise current. So this side is acting like south pole, this side is acting like north pole. So they'll attract each other. Solenoid undergoes a contraction. Whenever a current is allowed to pass through this, solenoid undergoes a contraction. And I even showed you a video, Rogers spiral. Do you remember this? An experiment, Rogers spiral experiment. You check it out on YouTube if you want. I actually showed this in one of the sessions. Okay, so whenever a current is allowed to pass through a solenoid has decrease in length. Solenoid will contract. I'll tell you the reason for it one more time. Why does the solenoid contract? Look at that. You know, when a current is allowed to pass through the solenoid, one face of the ring, you take one ring. This face of the ring, just imagine, has clockwise current. So the next side has anti-clockwise. Nearby faces, that means right face of first ring and left face of second ring will have opposite polarity. South pole and north pole. South pole and north pole attract each other. Tell me, whenever a current passes through a ring, it will act as a south pole. One face will act as south pole and the other will act as north pole. Look at this. If current goes in the anti-clockwise direction, that is a north pole. If current flows in the clockwise direction, that is a south pole. So if you take two rings over here, the right side of first ring is acting like a south pole. Left side of second ring is acting like a north pole. So they tend to attract each other. And this happens in all rings over here, which means what? As such, the solenoid undergoes a contraction. They say solenoid undergoes an expansion. So assertion is false. How about reason? Let us look at the reason statement. Read assertion once again. A solenoid tends to expand. That's wrong. Solenoid tends to contract when current passes through it. Then reason. Two straight parallel wires carrying currents in same direction. Same direction do what? Like charges repel, like poles repel, like currents attract each other. What do they say? Two straight parallel metallic wires carrying currents in same direction repel each other. That's false. So assertion is false, reason is false, answer is option D. Did you understand? Did you understand? Okay. Couple of more, we'll take the break, okay? 20-second question, we'll go for break after 20-second question. Read question number 21. In a conductor, free electrons keep on moving, but no magnetic force acts on the conductor in a magnetic field. In a conductor, free electrons keep on moving. In a conductor, this is conductor, right? Free electrons keep on moving. Yes, that's right. They are moving. This is like electron gas. This is like molecules in a gas taken in a container. The molecules are in random motion. Similar way, the electrons are in motion. Let's take this statement. In a conductor, free electrons keep on moving, but no magnetic force acts on a conductor. If it is placed in a magnetic field, will there be a force? Force will be zero. Can you tell me why? Because these electrons are moving randomly. So net transportation will be what? Random motion. Net value will be what? Zero. But if you connect this to a cell, things will be different. All these electrons will be aligned in a particular direction. There will be a current. Now there will be a current carrying conductor. There will be a force. Okay. Did you understand the difference? Read the question once again. 21st question. Statement number 1. Assertion statement. Read it for God's sake. In a conductor, free electrons keep on moving, but no magnetic force acts on the conductor in a magnetic field. In a conductor, they have said only in a conductor, not current carrying conductor. Current carrying conductor will be different. In a conductor, free electrons are moving randomly. That's true. Why? If you take a gas in a container, the gas molecules are in incessant motion, random thermal motion. Similar way, if you take a conductor, electrons are randomly moving everywhere, but will it create any current? No, net transportation is zero. Just imagine, children are running into the room, they are running out of the room. So if they do this randomly, the net number of students, change in number of students would be zero. Understood? We would assume that the number of outgoing students will be equal to the number of incoming students. Same way, 5 electrons are going up, 5 electrons are coming down. That is a case of probability function. Random distribution. Understood? That is based on probability. So net transportation will be zero. If current is zero, force will be zero. But if you connect this to a cell, things will be different, because now these electrons are moving in a particular direction, like this. All the current is flowing in this direction from positive to negative. Now there will be a current, there will be a force. But here, what you said about the assertion statement is true. No force is there. Reason: force on free electron due to magnetic field is always perpendicular to its direction of motion. Force on free electron due to magnetic field is always perpendicular to the direction of motion. Force on free electron due to magnetic field. Force on free electron due to magnetic field. Force is what? Q into V cross B. Free electron means what? E into V cross B. Yes, that is perpendicular. That's true. That's true. Reason is also true. Can you tell me why? But reason doesn't have got anything to do with assertion. So answer is option B. They have given C there. I don't know why. Anyway, answer is option B. Second statement is also true. Read second statement again. Check if I've gone wrong. Could you please tell me? Could you please help me? Question number 21. Read assertion. In a conductor. Oh, assertion is true. Already true. Let us check it out with reason. Force on free electron. Force on free electron due to magnetic field always acts perpendicular to direction of motion. Always acts perpendicular to direction of motion. So force is Q into V cross B. Magnetic force. Force is always force on free electron due to magnetic field always acts perpendicular. Yes, that's true, because force equal to Q into V cross B. Q is electron charge, that is C, into V cross B. This is cross product, right? Cross product, the components will be perpendicular to this, the resultant. Force will be perpendicular to V, force will be perpendicular to B. Do you know that? No. You learned A cross B direction in first year classes. If this is A, this is B, where is A cross B? A cross B is into the board, So my point is A cross B will be perpendicular to both A and B. That is the speciality of cross product. So V cross B is perpendicular to, F. V cross B. That F is perpendicular to what? F is perpendicular to V. F is perpendicular to B. Okay. There was a similar question board examination from electric dipole. I don't know whether you remember or not. We did this in class. Torque is equal to P cross E. Identify the pair of perpendicular vectors. Identify the pair of perpendicular vectors. Top perpendicular to P, top perpendicular to E. Pair of perpendicular vectors. That got repeated. Form paper question. Okay. So here, this is a cross product. And in cross product, answer will be perpendicular to component vectors. Answer is F, perpendicular to component vectors. F perpendicular to V, F perpendicular to B. What do they say in recent statement? Force on free electron is always perpendicular to direction of motion velocity. So that is true. Assertion is true, reason is true, but reason is not explanation for assertion. Assertion is something else, right? Assertion is something else. That has got nothing to do with reason. So answer is option B. Did you understand? Question number 22. Assertion, when a force is zero, all right. When a force is zero, question number 22, when force is zero, charged particle follows linear path. Okay, when force is zero, if force is equal to zero, Q into V cross B, this is force is equal to Q into V cross B. Okay, and if the force is zero, the charged particle follows linear path. Assertion is true. Question number 22. Assertion is true. Okay, and then a charged particle enters in a uniform magnetic field whose velocity makes an angle theta with the magnetic field will cover a linear path. I'll tell you. Look at this. Just imagine this is a magnetic field. This is a magnetic field, okay? And a particle is entering at an angle theta with a velocity v. Velocity can be split up into two components, v cos theta and v sin theta. Okay. Now v sin theta is actually into the board. It creates a circular motion because that is creating the Lorentz force. And this v cos theta is giving a linear motion. So the particle will move in a spiral path. This is called helical or spiral path. Helical or spiral path. Okay. This is for theta value 0 less than theta less than 90. 0 less than theta less than 90. Theta value should be in between 0 and 90. What if theta is perfectly 90? That means the particle enters perpendicularly. This component won't be there. V cos 90 would be 0. So only circular motion. Only circular motion. Only circular motion. We have done this in class. Only circular motion. What if theta is 0? If theta is 0, V sin 0 will be there. Only V cos 0 will be there. That means the particle will be moving in a straight line. Straight line. So let us look at it again. It's an important point. Yeah, I'm repeating this. We have a particle. Look at this. I'm repeating this. We have a charged particle. We have a charged particle. We have done this many times in class. This is what? This is a magnetic field. Okay? Magnetic field line. And a particle is entering at an angle theta with a velocity v. Then split that velocity into two components, v cos theta and v sin theta. Where is v cos theta? V cos theta is to the right. Where is v sin theta? V sin theta is into the board. And v sin theta is giving Lorentz force. Lorentz force causes circular motion. So the particle moves in a circle. And then this component is giving linear motion. This component, v cos theta, is pulling it to the right, which means it actually moves in a helical path. So 0 less than theta less than 90 for any angles between 0 and 90. For any angle between 0 and 90. If the particle enters at an angle, if a charged particle enters, what is the context? If a charged particle enters a magnetic field at an angle which satisfies 0 less than theta less than 90. That means theta value should be 0 between 0 and 90. Tell me what is the shape of the path? This is called helical path or spiral path. That happens when theta is equal to 30, 45, 49, 48, anything between 0 and 90. What if theta is equal to 90? When the particle enters perpendicularly, tell me, not at an angle theta, perpendicularly. This component will be V cos 90. Cos 90 is 0. So this component won't be there anymore. This component alone will be there, V sin 90. That is V. So that means only this component, that is only circular motion, only circular paths. Then what if it is theta equal to 0? The particle enters parallelly. Tell me what? The particle enters parallelly, theta is 0. You put sine 0, V sine 0, 0. So this component won't be there. V cos 0 is 1. So V. That component alone will be there. So this component alone means the particle moves in linear paths. So there are three cases again. I'll repeat. Whenever a charged particle is shot into a magnetic field, there can be three cases. Okay, first one, at an angle that is in between 0 and 90. 0 less than theta less than 90. So that means angle is in between 0 and 90. In such a case, the particle will have two components. One is V cos theta along the direction of field. Second is V sin theta perpendicular to the direction of field. So these components are giving two motions. This component is giving a circular motion, while this component is giving a linear motion. So the combined path will be helical path or spiral path. When theta is 90, that means the particle enters perpendicular to the field. This component won't be there. V cos 90 is 0. This component alone will be there, V sin 90. That makes it what? Only circular motion. On the other hand, if this component is there, not there, and this component alone is there, that means the particle enters parallelly. Theta 0, V cos 0, 1, V cos 0, 1. So it is V. The particle has 0 component here. The particle goes to the right, only in a straight line path. So let us read the statement again, 22nd statement. Question: when the force is 0, the charged particle follows linear path. Force is 0, charged particle follows linear path. That is true. Force is 0. Force is Q, V, B sine 0. That is 0. Force is 0. Then the particle follows a linear path. Assertion is true. Reason: a charged particle enters a uniform magnetic field whose velocity makes an angle theta with the magnetic field will cover a linear path. Wrong. Reason is false. Why? It is not. If it is entering at an angle theta, it is executing spiral path or helical path. Spiral path or helical path. Assertion is true. Reason is false. Answer is option C. What does the second statement say? Again, a charged particle entering a uniform magnetic field with a velocity making an angle theta with magnetic field. Theta. If it is making an angle theta, it's a non-zero angle, non-90 angle. It obviously creates what? A helical path. Executes a helical path. But what they say is a straight line path. That's wrong. Answer. Reason is strong. Assertion is true. So correct answer is option C. Did you understand? I'm asking everyone, tell me please. Question number 23. Assertion: when a current is represented by a straight line, the magnetic field will be circular. That is true. When a current is represented by a straight line, the magnetic field lines will be circular. Do you remember? Concentric field lines. Am I correct? Read that again. Question number 23. Assertion: when a current is assertion, then reason. When a current is represented by a straight line, the magnetic field lines will be circular. Yes, current is represented by a straight line. The magnetic field lines will be circular, right? Because if you hold the conductor in your right hand with the thumb in the direction of current, other fingers, curled fingers, will give you the direction of magnetic field. Do you remember? If you wrap the conductor in your right hand with the thumb in the direction of current, look at this. The curled fingers, the wrapped fingers will give you the direction of magnetic field. So here it is going into the board, here it is coming out of the board. Okay, I even told you one shortcut, LORI. If you walk along this current, on your right side, field is inward. Field is inward, inward, inward. On your left side, the field is outward. Outward, outward, outward. So here it is going into the board, here it is coming out of the board. So they are in concentric circles. So statement 1 is correct. Assertion is correct. Let us check reason now. 23. According to Fleming's left-hand rule, the direction of force is parallel to magnetic field. Question number 23. According to Fleming's left-hand rule, direction of force is parallel to magnetic field. That's wrong. Because Fleming's left-hand rule says what? I into L cross B, right? The force on a conductor is given by I into L cross B. L cross B. Is force parallel to magnetic field? No. Fleming's left-hand rule is for what? Do you remember? FFCCTT? Do you remember Fleming's left hand rule? If the first finger is, hold the first 3 fingers of your left hand in 3 mutually perpendicular directions. You learned this in class 10 also. Hold the first 3 fingers of your left hand in 3 mutually perpendicular directions like this. First finger represents field, central finger represents current, then thumb represents thrust. F, F, C, C, T, T. If the first finger represents field, F, F, central finger represents current, then the thumb represents thrust, direction of motion of the conductor. Anyway, that gives you force on a conductor I into L cross B. Force is equal to I into L cross B. What does the statement number 1 say? Could you please read it? Statement number 1. When current is represented by straight line, the magnetic field will be circular. That statement is true. Assertion is true. How about reason? According to Fleming's left-hand rule, direction of force is parallel to magnetic field. Direction of force is parallel to magnetic field. Is that true? No. We have just learned this now. The cross product. If you take the cross product, the result will be perpendicular to both the component vectors. So F is actually perpendicular to L. F is perpendicular to B. So force and B are perpendicular. Here they say they are parallel. So that is false. Assertion is true. Reason is false. Answer is option C. Did you understand? I'm asking everyone. Did you understand? Assertion is what? When current is represented by straight line, field lines are circular. That's true. Concentric circular field lines. Then according to Fleming's left-hand rule, Fleming's left-hand rule you've been seeing since class 10. That is to give the force on a conductor, I into L cross B. Force is perpendicular to B because cross product, no? Both the component vectors will be perpendicular to force, resultant vector. But here they say the force is parallel to magnetic field. That's wrong. So let us look at the next one now. Question number 24. Let's make it quick. 5 more questions. We'll finish in no time. Right. 24. An electron and a proton enters a magnetic field with equal velocities. Then force experienced by the proton will be more than that of an electron. So assertion statement, then reason statement. Let us see one by one. What is question number 24? An electron and proton enter. An electron and proton enter a magnetic field with equal velocities. So what is the force on it? Q into V cross B. Q into V cross B, right? For electron, tell me electron, how do we write it? Electrons force on electron. That is F vector is equal to minus E into V cross B. Minus E into V cross B, right? Because electron charge is minus E. And then proton charge is positive. So F is what? It is plus C into V cross B. Only the directions are different. Look at that. Directions are different, right? One is minus E into V cross B. The other is plus C into V cross B. The directions are different. What do they say in the question? An electron and proton enter a magnetic field. Enter a magnetic field with equal velocities. Then the force experienced by proton will be more than that of an electron. No, they are numerically equal. Electron charge and proton charge are equal. They enter with the same velocity. So V is same. They enter the same magnetic field. B is also same. So assertion is false. They say proton experiences more force. That's wrong. Absolutely wrong. Mass of proton is 1999 times more than that of electron. That is also false. Answer is option D, because mass of proton is approximately 10,000 times, actually greater than 10,000 times mass of electron. Okay, mass of proton is 1.6 into 10 power minus 27. Mass of proton is what? 1.6 into 10 power minus 27. Mass of proton is 1.6 into 10 power minus 27. This is also called 1 atomic mass unit, 1 U. Mass of a proton, 1.6 into 10 power minus 27. Mass of electron, it is 9.1 into 10 power minus 31. Look at the power, 4 zeros, right? That is roughly 10,000. Okay, if you forget about the multiplier here. Okay, forget about the multiplier. Look at the size of the power there. So when you compare 27 and 31 are differing by 4. So 10 power 4, 10,000 times. So mass of proton is greater than 10,000 times mass of electron. So that statement is also false. Let me repeat that. An electron and proton enter a magnetic field with equal velocities. Electron and proton, what is the force experienced? Q into V cross B. Q is, for electron it is minus C. Charge of electron is minus C. For proton it is plus C. Charge is the same, no? Both are entering with same velocity. V is same. Both are entering same magnetic field. B is also same. So forces are same. They say proton experiences more force. Force experienced will be more than that of an electron for a proton, right? That is wrong. Assertion is wrong. Reason says that mass of proton is 1999 times more than that of electron, but that is wrong. Mass of proton is 10,000 times greater compared to that of electron. Assertion is false. Reason is false. So answer is option D. Hope you understood this. If you have any questions, you can ask me now. Otherwise, we'll move to question number 25. Magnetic field. Question number 25. Assertion. Assertion. Question number 25. Magnetic field is useful in producing parallel beam of charged particle. Magnetic field lines inhibits motion of charged particle moving across it. Okay, magnetic field is useful in producing a parallel beam of charged particle. Magnetic field is useful in producing a parallel beam of charged particle. Yes, that is called velocity selector. You remember, there is a plate at the top, there is a plate at the bottom. Okay, so I have a particle, say electron. Imagine an electron or a proton is entering this. What will happen if I have positive plates here? No, positive plate at the top and negative plate at the bottom. Tell me what? This proton being positive will be repelled by positive, attracted by negative. So it has a force in the downward direction, QE. At the same time, if I apply a magnetic field, look at this. Let me see 1 second. Yes, that will experience a force in the upward direction. And that force is called QVB, Lorentz force. And these two forces, if they can balance each other, this particle will go in a straight line. This is called velocity selector. And the condition for velocity selector is what? QE should be equal to QVB. Or Q and Q are cut, V will be equal to E by B. Hope you remember this. This is the concept of velocity selector. I'll repeat one more time. On the roof, it's full of what? Roof is full of positive particles, positive charge, and the floor is full of negative charge. And into this region, you are shooting a proton, and then what's happening to the proton? What happens to the proton? The proton experiences two forces because proton has positive charge already, right? So it experiences an electric force. This plus plate is repelling proton in the downward direction. Minus plate is attracting proton in the downward direction. Okay, so the electrostatic force is downward, QE, electrostatic force QE. What about magnetic force? If you apply a magnetic force perpendicular to this, look at that. This is called crossed magnetic field, cross fields. These are called cross fields. Particle is moving along x-axis. Electric field is applied in y direction, and magnetic field is applied in the z direction. They are in mutually perpendicular directions. Look at the directions again. Where is the particle going? The particle is moving along x-axis. The particle is moving to the right. The particle is moving along x-axis. Where is the electric field? Electric field from positive to negative, positive, negative, positive, negative, positive, negative, positive, negative. So it is in the downward direction. So particle moves. Velocity is in x direction. Velocity is in x direction. The particle is moving in y direction. Electric field is in y direction, negative y direction. It is downward. And then magnetic field is into the board. These are all into marks, into marks, into mark. Into the board means minus Z. Out of the board is plus Z, into the board is minus Z. Look at that. This is called velocity selector, the concept of velocity selector. Look at that. You know, the particle is moving along x-axis. So velocity vector is in x direction. And then electric field is in negative y direction. Electric field is downward. And magnetic field is in negative z direction. It is into the board. These are all into marks you see here. Right. So anyway, they are mutually perpendicular. If one is on x-axis, the other two are on y and z axis. Understood? If particle is moving in y direction, electric field is in x direction and magnetic field is in z direction. These are called crossed fields. They are like crossed fields. Okay. And anyway, the condition is this QE should balance QVB. If they balance each other, net force would be 0. The particle would go in a straight line. If you cut this Q and Q on either side, you're getting V is equal to E by V. That is a condition of velocity selector. Let's get back to the question now. Question number 25. Magnetic field is useful in producing. Parallel beam of charged particles. Parallel beam of charged particles. That's right. Assertion is true. You can get a parallel beam of charged particles. Parallel beam, no? That can pass through a small hole here. This is called velocity selector. How about recent statement? Magnetic field inhibits the motion of charged particle moving across it. Yes, that's also true. Magnetic field actually deflects the particle. That is why it happens, right? So assertion is true, reason is true, and reason correctly explains assertion. Answer is option A. I'm explaining that one more time. Question number 25. Read it again. Question number 25. Magnetic field is useful in producing parallel beam. That is true. Reason. Magnetic field inhibits the motion of charged particle moving across it. Magnetic field actually causes the deviation of the particle, right? And that is balanced by electric force, right? That is why it happens. So answer, assertion is true, reason is true, and reason explains assertion, because reason statement has been used in explaining assertion. Understood? This happens because of the deviation for the particle. That happens, that is arising out of what? Lorentz force. Did you understand? So let's look at question number 26 now. There are 5 more questions to be done very quickly. Question number 26. Assertion. When a magnetic dipole is placed in a non-uniform magnetic field, only torque acts on the dipole. Force would act on the dipole if a magnetic field is uniform. I must have told you at least 3 times in class this question. This question got repeated 8 times in entrance examinations, okay? And this got repeated many times in board examinations also. I'll tell you. Look at this. I don't know whether you remember or not. This is applicable for uniform and non-uniform magnetic and electric dipoles. Look at this. This is a electric field. I'm doing this with electric field, and then I can extend that to magnetic field. And I keep a dipole here. This is plus Q and this is minus Q. This has a force to the right QE. This has a force to the left QE. Now these forces would tend to create a torque. So torque will be not equal to 0. How about force? Project this force to the center of mass. Project this force to the center of mass. They are equal, as you can see. QE to the right, QE to the left. So force will be equal to 0. This is a case with uniform field. What if it is non-uniform field like this? Look at this. I have the dipole kept here. This force is QE. This force is QE dash. Okay. Now the forces are different because the field is different at different points. That is a non-uniform field. So it has a torque. Torque is not equal to 0. How about force? Is at 0. Project this at the center of mass. Project this force at the center of mass. Will they cancel? No, they are never going to cancel. So force is not equal to 0. Torque not equal to 0, force not equal to 0. This is a very, 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 very important point. Many times I've told you. I'm repeating. Whenever this is actually, I've done this with electric dipole, but this is possible with the magnetic dipole also. We did in both cases. Electric uniform field. This is non-uniform field. Non-uniform field. Whenever a dipole is placed, electric or magnetic, whenever a dipole, electric dipole or magnetic dipole, is placed in an electric field or magnetic field, this thing will happen. Which thing will happen? This is a uniform field. If you place it in a uniform field, the force here is QE to the right, force here is QE to the left. Together, they'll create a couple. Couple is called torque. So torque is not equal to 0. PE sine theta. It is MB sine theta for magnetic dipole. How about force? Take this out to the center of mass, force to the right. Take this out to the center of mass, force to the left. They are equal and opposite. They will cancel each other. Force will be 0. Check the notes. On the other hand, if it is kept in a non-uniform field like this, look at that and tell me non-uniform field. The force here is QE in this direction, and the force here is QE dash in this direction. These forces, they together create a torque again, torque. What about force there? Will they cancel? This force is here. Look at the force. Look at the force. This force is kept here. This force is kept here. Will they cancel? No. Those forces are never going to cancel. So the net force would not be equal to 0. Let's go back to the question and analyze. Could you please take the paper? Okay, what is given in the paper? What is given in the question? When a magnetic dipole is placed in a non-uniform field, only torque acts on the dipole. Only torque? No, torque and force act. Only torque. So assertion is false. So how about reason? Let us check reason. Force would act on dipole if magnetic field is uniform. Magnetic field is uniform. Force would act. Would force act? No, force is 0. So reason is also false. Answer is option D. This is supposed to be the most important question in today's discussion. Okay. Did you understand this? If not, please tell me. I can repeat that. Tell me, please. See, first statement was about what? First statement was about. Oh. First statement, when a magnetic dipole is placed in a non-uniform field, look at that, non-uniform field, only torque acts on the dipole. Is that only torque? No, 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 no. Force also acts, F not equal to 0. So that statement is wrong. Assertion is false. How about reason? Force would act on dipole if magnetic field is uniform. Magnetic field is uniform. Will force act? Force wouldn't act. So if it's not equal, if it's equal to 0, so that statement is also wrong. Assertion is 0. Assertion is wrong. Reason is wrong. So answer is option D. Let's go back to question number 27. Right. There are 4 more questions. I'll quickly do that as quickly as possible. Okay. You will have to cooperate. I might extend by 2-3 minutes. Okay. Right. Maximum 5 minutes. Question number 27, 28, 29, 30. 27. Magnetic moment is measured in Joule per Tesla or Ampere per meter square. Magnetic moment. Do you remember? Magnetic moment is written as I into A, current into area. Okay, current into area. And what is the unit for current? Ampere. What is the unit for area? Meter square. Ampere meter square. And there is another unit that is Joule per Tesla. Joule per Tesla. Okay, you can get this from which equation? You remember the equation for potential energy? U is equal to mb cos theta. Then what you need is dipole moment. M will be U is Joule by B is Tesla. Cos theta doesn't have any unit. Do you understand? No. See, what is the question? 27. Magnetic moment is measured in Joule per Tesla or Ampere meter square. Ampere meter square. Let's check. Magnetic moment equation is what? Current into area. For a loop, for a current carrying loop, magnetic moment is NIA. N is the number of turns. But if N is 1, there is only one turn, there is only one circle. It is current into area. Current is measured in ampere. Area is measured in meter square. So ampere per meter square is 1 unit. Okay. And then second statement is what? Second is what? Joule per Tesla. Potential energy equation. You remember this? Minus mb cos theta, minus pe cos theta. Similar way. So U is equal to minus mb cos theta. We have written this in class. What I need is EM. I'll keep it there. U by B. U by B. Cos theta is not to be taken. Cos theta doesn't have any unit. Cos theta is a trigonometric function. It doesn't have any unit. So U is energy, which is Joule. Then B is magnetic field, which is Tesla, Joule per Tesla. So assertion is true. Reason, how about reason? Joule per Tesla is equivalent to ampere meter square. That is also true. Joule per meter and ampere Tesla, ampere meter square, Joule per Tesla and ampere meter square are equal. So both are correct. And then first one is explained by the second one. So answer is option A. Assertion statement is correct. Reason statement is correct. Reason is the explanation for assertion. Because in assertion, we say it could be either ampere meter square or Joule per Tesla. And that is because both are equivalent. That is what the second statement says. Did you understand? Answer is option A. Did you understand? Please, please, please tell me. Okay, right. So answer is option A. Assertion is correct. Reason is correct. And if you check reason, if you analyze it carefully, that is the reason for statement number 1. They are equal. Joule per Tesla and ampere meter square are equal. That is why we are measuring with Joule per Tesla or ampere meter square. It's fine. Question number 28. The kinetic energy of charged particle moving in a uniform magnetic field does not change. Kinetic energy of a charged particle. Yes, I told you the reason. Whenever a particle enters a magnetic field, tell me what? It executes circular motion because the particle is acted upon by a Lorentz force, which is acting as centripetal force. Now, speed. What happens to speed? Speed does not change. Doesn't change. Speed doesn't change because this is centripetal force. Centripetal force can change only the direction, not the magnitude. Speed will not change. Lorentz, whenever a charged particle is shot into a magnetic field, you know, it is acted upon by a Lorentz force. Lorentz force acts as centripetal force. Centripetal force is to the center. But this force cannot change the magnitude. That means speed cannot be changed. Speed will still be the same, but velocity will be different. Velocity will change. Tell me why? Because velocity changes because the direction changes. Direction change is actually caused by the centripetal force. Centripetal force can change only the direction, not the magnitude. So if speed doesn't change, kinetic energy doesn't change, because kinetic energy is half m square, half m speed square, half m v square. That v is not velocity, it is speed, half m speed square. So statement A, kinetic energy of a charged particle moving in a uniform magnetic field does not change. Assertion is true. It doesn't change. Reason: in a uniform magnetic field, no force acts on the charged particle. In a uniform magnetic field, no force. No. Is that what we've been doing? You know, force acting is what? QVB sine theta. So that is false. Assertion is true. Reason is false. Answer is option C. Again, one more time. Look at that. Question number 28. The kinetic energy of charged particle does not change. That's true. That's a previous board question. Show that it does not change. It's a previous question. Assertion is true. Reason says what? In a uniform magnetic field, no force acts on charged particle. That is absolutely wrong. Because whenever a charged particle enters a magnetic field, Lorentz force acting as QVB sine theta. QVB sine theta. So assertion is true. Reason is wrong. Answer should be option C. Hope you understood this. We have 2 more questions to go. I'll quickly finish them and wind up. Okay. Question number 29. Hope it's okay for everyone. 29. A charged particle moving in a uniform magnetic field penetrates a layer of lead and thereby loses half of its kinetic energy. A charged particle moving in a uniform magnetic field penetrates a layer of lead and loses half of its kinetic energy. The particle is this, and upon losing, its kinetic energy decreases to E by 2. The radius or curvature of its path is now reduced to half of its initial value. What is the equation for kinetic energy? Do you remember the equation for kinetic energy? Q square B square R square divided by 2m. Do you remember? Should I do that? We have done this at least 100 times in class. What is the kinetic energy of a particle entering a magnetic field? You know how to formulate this. I even told you the technique to formulate this equation. Do you remember? We did this revision twice in class, the revision numericals. Tell me, kinetic energy of a particle is Q square B square R square by 2m. Now, what about kinetic energy? Is proportional to R square. Look at this, R square. Now look at the question, assertion statement, and say if it is correct. A charged particle moving in a uniform magnetic field penetrates a layer of lead and thereby loses half of its kinetic energy. The radius or curvature of its path now reduces to half of its initial value. Is that correct? Wrong. Why? These are actually proportional with square, right? If E is proportional to R, you know, when E becomes E by 2, R becomes R by 2. But here E is proportional to R square. They are not directly proportional. So assertion is false. How about reason? Kinetic energy is inversely proportional to radius of curvature. That is wrong. Assertion is false. Reason is false. Answer is option D. Did you understand? Say something, please. I'm asking everyone. Towards the end, I rushed a bit, I know, but I have no other option. Okay. I need to finish. AC questions, few AC questions still remain, but I'll quickly explain that one more time. What do they say? A charged particle moving in a uniform magnetic field penetrates a layer of lead. The particle penetrates a layer of lead and thereby loses half of its kinetic energy. It lost its half kinetic energy inside in overcoming the friction. So its energy is E. Its energy here is E by 2. So here, if it describes a circle of radius R, here it describes R by 2. That's what they say. Is that correct? Kinetic energy equation is what? Q square B square R square by 2m. As you can see, E is proportional to R square, not R. Had R been R, you know, had this been R, E proportional to R, that would have been correct. When kinetic energy decreases to half, R decreases to R by 2. That's correct. Correct? When this becomes E by 2, this becomes R by 2. That would be all right, because all others are constants here. Charge is constant, magnetic field is constant, mass is constant, 2 is constant. So Q is proportional to R square. R. If it is E is proportional to R, but here E is proportional to R square. So it doesn't change to R by 2. Understood? So that statement is false. Second statement is what? Kinetic energy is inversely proportional to radius of curvature. Is that correct? No, kinetic energy is directly proportional to r square. So reason number 2 is wrong. Answer is option D. Assertion is false, reason is false, answer is option D. The last question here, question number 30. Look at question number 30. A charge, whether stationary or in motion, produces a magnetic field around it. That's wrong. What is the name of the chapter? Moving charges and magnetism. Moving charges and magnetism. Only moving charges can create magnetic field. So you can just write this down. This is an important point. Write this point. Stationary charge. Stationary charge. It produces electric field. Electric field. Electrostatics. Moving charge. Uniformly moving charge. Moving charge produces electric field and magnetic field. Electric field and moving charge produces magnetic field. Simply magnetic field is fine. Moving charge produces magnetic field. Third one, accelerated charge. You remember this? Accelerated charge produces EM wave. EM waves. You have to write these 3 points. This is very, very important. Stationary charge produces electric field. Uniformly moving charge. Uniformly moving charge means at same speed. That will produce magnetic field. Okay. Stationary charge produces electric field. Moving charge produces magnetic field. And accelerated charge. Accelerated charge produces electromagnetic wave. Bohr's postulates. Check it out. Why did Rutherford theory fail? Because it's a circular path. The particle is moving in an orbit and it loses energy because it is continuously emitting waves. That time I told you, accelerated charge always emits electromagnetic wave. So statement number A, assertion statement. Tell me, a charge whether stationary or in motion produces magnetic field around it. No. Stationary charge can never produce a magnetic field. So assertion is false. What about reason? Moving charge produces only electric field in the surrounding space. No, moving charge produces both electric field and magnetic field. So that is also false. Answer is option D. I'll quickly repeat that one more time. Just keep this in mind. A stationary charge produces electric field. Stationary charge produces only electric field. Moving charge produces magnetic field and electric field. Moving charge produces magnetic field and electric field. Actually, this part you don't need to know, but since that is mentioned in the second statement, I'm just mentioning it. B and D. Accelerated charge produces electromagnetic wave. Let us read the statements again. A charge, whether stationary or in motion. Charge, whether stationary or in motion, produces magnetic field. No, stationary charge can never produce magnetic field. Zero. Right. So assertion statement is false. Reason, moving charges produce only electric field in the surrounding space. That is wrong. Moving charges produce magnetic field as well as electric field. So that is also false. Assertion is false, reason is false. So answer is option D. Did you understand everything we learned today? That's all about magnetic effects of current.